Hello, in this video we will learn how to enumerate the PCI bus to get the devices on the PCI bus and then display their vendor IDs and device IDs to the screen. This is leading up to the next video where we will be able to actually start printing some information about the PCI devices we have, but this is a good start. Also, just one more thing, if you've been enjoying this series, then be sure to leave a like and a comment. Every little bit helps to boost that YouTube algorithm. I also wanted to say thank you to my patrons. So thank you to Bobby Addison, Jim Borden and Rizix for the tier 2 subscription, and thank you to Kenneth Looney for the tier 1 subscription. Now, let's get started. So now we have PS2 keyboard and mice set up, but that's not really useful on modern PCs as the PS2 port has been outdated. Nowadays, most PCs use USB mice and keyboard, so we're going to have to create USB drivers for those. To get access to the USB host controller to create the driver for the USB keyboard and mouse, the first thing we have to do is go through the PCI bus and find all of the devices located on there. But to get to the PCI bus, we have to find the root system description pointer from the UEFI bootloader and then find the MCFG table. So to get started with that, we're going to need to jump back into the source of our bootloader and change a few things. So here we are back in the source of our bootloader. We're going to need to add one more variable to our boot info struct. So here we are with our boot info struct. We need to add a void pointer to the RSDP, which is our root system descriptor pointer. Now that we have that value there, we can actually use the UEFI protocols to fetch the RSDP and then hand that over to our kernel. So right after we get the EFI memory descriptor, we can now get the RSDP. So we can find the RSDP on the configuration table, which is a table contained within the system table. So we can do EFI underscore configuration underscore table pointer config table equals system table configuration table. Now we need a variable to store our RSDP, so void pointer RSDP equals null. And we're going to be searching for the ACPI 2.0 root system description pointer. So we need the EFI underscore GUID ACPI 2 table GUID equals ACPI underscore 20 underscore table underscore GUID. Now we need to loop through the configuration table and find the ACPI table. So for uint n index equals 0 index less than system table dot number of table entries index plus plus. Now we can do if compare GUID. Now we need the address of the config table indexed by index dot vendor GUID, comma, and then we need the address of our ACPI 2 table GUID. So now we're comparing these two GUIDs, and if they are the same, then we've found the ACPI 2 table. Now we need to check if the signature of the table that we've just found is RSD space PTR, indicating that it is actually our RSDP. So to do that, we need to create a string compare function. So we'll scroll up to some empty space and we'll create our string compare function now. So that's uint n strcmp for string compare. And now we need a char8 for our input, which is A, and then we need a char8 pointer for our second input, which is B. Now we need a uint n length, and we can do for uint n I equals 0, I less than length, I plus plus. If dereference A does not equal dereference B, we can return 0, otherwise we can return 1. So when we return 1, that means it successfully compared all of the characters in the string, and if we return 0, that means it's failed. So now we can do if string compare constitute a char8 pointer, quotation mark RSD space PTR space, all capitals, and it is important to have that space at the end, comma, constitute a char8 pointer config table vendor table. And of course, we need to put in the length of the string, so that's 8. So if the strings are equal, then we can set our RSDP. So RSDP equals casted to a void pointer config table vendor table, and then we can break. But if neither of these are true, we just need to increment our configuration table, so config table ++. Alright, now in our boot info, so boot info.rsdp equals RSDP. Now we should be able to go back to our kernel and analyze the RSDP, and it should be the correct pointer. Actually, something interesting I just noticed, and something that was causing me a bug, is that if we break once we find the first RSDP, then it will cause a general protection fault because we're not actually getting the correct ACPI table. So if we remove this break and wait until we get the last instance of the RSDP, then everything works fine. I'm not sure why this is happening, but it is something that I have to do to get this to work. If you have any idea why this is happening, please let me know in the comments. So we just need to make that quick fix in our bootloader and then recompile the bootloader and rebuild the image. So now we're going to have to go to kernel-util.h and change our boot info struct to a void pointer RSDP so that we can actually access the RSDP within our boot info. And now we can do something like global renderer.next. So we go to the next line after kernel initialize successfully, and then we can do global renderer.print to hstring boot info.rsdp casted to a uint64. Alright, now we can compile that and see what happens. Just remember to clean your lib folder, so delete that so it recompiles everything, because we've changed the struct in the header, and we're also going to have to recompile our bootloader. So go into our GNU EFI directory and type make bootloader. And now, as you can see, we have kernel initialized successfully, and then we have our address of the RSDP. Now we can actually prove that this is the RSDP, the root system description table, by printing the signature, which is the RSD space PTR that we checked for in the bootloader. So we'll go back to our source and we'll do global renderer next to go to the next line. Then we can do global renderer dot put char dereference casted to a uint8 pointer boot info RSDP. And we can copy that again, and then we can do put a bracket around RSDP and its cast and do +1, then +2, then +3, then +4, +5, +6, and +7. Now, of course, you could do this as a for loop instead if you just wanted to make it a little bit simpler, but just as a proof of concept, this will work just fine. Now, as you can see, we have printed RSD space PTR, so we've successfully located the RSDP. Now, using this root system descriptor table, we will be able to locate many other system tables, which will be very beneficial for doing things such as interacting with our hardware and even just detecting what hardware we have on our system. Alright, now that we have the RSDP, we can actually do something with it. So I'm just going to delete all of this signature printing code, and I'm going to create a new header file called ACPI.h. Inside that header file, we'll do pragma once and include standardint.h. And now I'm going to create a namespace, so namespace ACPI, and inside of here we're going to contain all of the functions and structs that are related to the ACPI tables. So the first one we have is the RSDP struct. So we have a struct RSDP, and we're using the RSDP2 because that's the one we found in the bootloader. And we're just going to make sure that this has the packed attribute to make sure that it is packed correctly. Alright, so the first part of the RSDP2 struct is the unsigned char signature array of size 8. And that is the RSD space PTR signature that we printed on the screen before. The next one is the checksum. Now this is a value that we can use to make sure that the table is correct, to make sure it's not corrupted or anything. The next one we have is the OEM ID, so OEM ID, which is an array of 6. The next one we have is a uint8 revision. Then we have a uint32t RSDT address. Then we have a uint32t length. Then we have a uint64t xsdt address, which I believe is the extended system descriptor table. Then we have the uint8t extended checksum. And then we have 3 bytes at the end, which are just reserved. So uint8t reserved, and it's an array of size 3. Now the tables that we're using, these system descriptor tables, they all have the same header, so we can create a struct called the SDT header, and this one will have the same packed attribute. And inside this SDT header, it is quite similar to the RSDP2, but we have an unsigned char signature, which is an array of size 4 rather than an array of size 8. Then we have a uint32 length, which is the length of the system descriptor table. We have the uint8 revision, the uint8 checksum, the uint8 OEM ID, which is an array of size 6, a uint8 OEM table ID, which is an array of size 8, uint32t OEM revision, uint32t creator ID, and a uint32t creator revision. The next struct that we need to make is the MCFG header. So the MCFG is the table that contains all of the information about the PCI bus. So we'll create that. So the struct MCFG header. The MCFG header contains the SDT header because it's a system descriptor table. So SDT header, and then it just says a uint64t reserved bytes. So it's very similar to the SDT header, except it has 8 reserved bytes at the end. And we just need to set the same attribute for the MCFG header as well, just to make sure that it's all packed accordingly. Alright, so now that we have all those structs set up, we can use them to go through the RSDP to find the MCFG and all the other system descriptor tables for that matter. So inside kernel-util.cpp, we can create a new function, prepare ACPI, and of course the function needs to be declared void. And this prepare ACPI function needs our boot info struct, well, the pointer to our boot info struct. And just for testing, we're not going to keep it like this way, but just for testing, first thing we'll do is prepare ACPI boot info. We're going to print all of the system descriptor tables to the screen just to see what we're dealing with. So we have the ACPI : just make sure that you have included ACPI.h in your kernel-util.h. So we just need to make sure that we include ACPI.h in kernel-util.h. And now we can do ACPI : SDT header pointer xSDT equals our casted to an ACPI : SDT header pointer bracket RSDP dot xSDT address. Now this doesn't work just yet because our RSDP is still a type of void pointer, but we can now turn this into our RSDP2 pointer. So in kernel-util.h, instead of doing void pointer RSDP, we can do ACPI : RSDP2. This needs to be bootinfo.rsdp.xsdt address. Make sure we have a lowercase b. And also make sure that we spell xsdt correctly with the correct capitals. Alright, now that that's working, we've got the xsdt. We can print all of the tables that the xsdt contains. So we can do int entries equals bracket xsdt.length. Take the size of the SDT header, the ACPI SDT header, exit those two brackets divided by 8. So what we're doing is getting the length of this table, taking away the SDT header, and then dividing it by 8, and we're left with the amount of entries that we have in the XSDT, because the entries for the tables come directly after the header for the XSDT. So that's pretty easy to figure out. Now we can just do for int t equals 0, t less than entries, T++. Now we can figure out the location of our new SDT header. So ACPI ::SDT header pointer new SDT header equals casted to an SDT header pointer, dereferencing a uint64t pointer, 2 brackets, casting to a uint64 xSDT, plus the size of the ACPI ::SDT header, plus bracket t times 8. So what we've got here is pretty messy, but basically what we're doing is casting the address of the xSDT to a uint64 so that we can do some integer maths on it, adding the size of the SDT header so we get the address of the end of the xSDT header, and then adding on t times 8 to get the address of the new SDT header. And then once we get that address, we just dereference it from a uint64t pointer into an SDT header. Then we can print its signature to the screen. So for int I equals 0, I less than 4, I plus plus, global renderer dot put char new SDT header dot signature indexed by I, and then after that second for loop we can do global renderer dot put char space, and now we've got that, we should be able to print all of the system descriptor tables contained inside the xSDT to the screen. So afterwards we'll just do global renderer dot next, and now we can compile that and see what we get. Alright, so now you can see we have the FACP, the APIC, the HPET, and the BGRT tables. Now the table that we're looking for is the MCFG table. However, QEMU doesn't have that on the default configuration, so we're going to have to tell it to use a different machine. So inside of our run script, when we are invoking the call to QEMU system x86_64, we just need to add -machine q35. Now thank you to Borden in the Discord for pointing this out, as I wouldn't have been able to find it without that tip. Now if we run that again, you can see that we have all of the other tables, but we also have an MCFG table as well, with that new -machine q35 flag that we used to run it. Now that we know that all of the tables are in place, we can create a function to get a specific table. So in ACPI.h, we can scroll down to the bottom and create a new function, and this one returns a void pointer find table, and you probably guessed it, but this function finds a specific table, SDT header pointer SDT header, and char pointer signature. Now we need to create a new file, ACPI.cpp. In that file we need to include ACPI.h. Then we need to add our namespace, ACPI. Now we can create the implementation for that function, so void pointer find table, SDT header, pointer SDT header, char pointer signature. And now we can do similar to what we did in kernel-util.cpp. We can just copy this little code here, which iterates through all of the tables, paste that in there, and we can replace this xSDT length with the SDT header, and we can change this xSDT to the SDT header as well, and we can get rid of this for loop and the global renderer calls. Now we can check the signature, so for int I equals 0, I less than 4, I plus plus, if new SDT header signature indexed by I does not equal signature indexed by I, we can break, and if t equals 3, meaning that the SDT header's signature equals the signature that we're passing into this function, we can return SDT header, return new SDT header I should say. Then at the end of the for loop, if it did not get a proper SDT header, we need to return null, which is just returning 0. Alright, now we can use this find table function to get the MCFG table. This actually needs to be if I equals 3 and not if t equals 3. Because if t equals 3, then that really shouldn't work. It does work, but it really shouldn't. And it might cause some unexpected behavior down the line. So just change that to if I equals 3, and we should be right. So we'll get rid of all of this. And we can write ACPI : MCFG header pointer MCFG equals casted to an ACPI MCFG header pointer ACPI : find table XSDT, comma, char pointer, quotation mark, MCFG. Right, then we can print to the screen the address of our MCFG, so global renderer print to H string, casted to a uint64t, our MCFG, and then we can do global renderer.next. And now we should have the location of our MCFG table on the screen. Alright, so as you can see, we have this address FB7E014, which is the address of our MCFG table. We can prove that it's the address of our MCFG table by printing its signature to the screen, so we'll do that now. For int t equals 0, t less than 4, t plus plus, global renderer put char MCFG dot header dot signature indexed by t. And as you can see, we have printed MCFG to the screen, so we've successfully found the MCFG table. So that's good. Now we can use the MCFG table to find information about the PCI bus. And to do that, we need to create a separate set of source files called our PCI.h and PCI.cpp. So let's create those now. PCI.h and PCI.cpp. Inside of PCI.cpp, we include PCI.h, and inside PCI.h, we do pragma once and include standard int.h. And we can create a namespace, PCI, and we can create a function called enumerate PCI. And we can take a pointer to our ACPI XSDT table, so include our ACPI.h. Then we need to take a ACPI : SDT. No, we need the MCFG table, not the XSDT table, sorry. So we need a pointer to our MCFG. Now in PCI.cpp, we can create the implementation for that. So we can copy all that and do our curly brackets. Right, now to go through the PCI bus, it's actually a little bit more complicated than it sounds, because there is many buses, and on each bus there is many devices, and in each device there are many functions, and we need to enumerate through all of those. So we're going to need a couple functions. So void enumerate bus, and this takes a uint64t base address and a uint64 bus. So this base address is the PCI base address, and this bus is the number of the bus that we are iterating across. And then we need the void enumerate device, which takes the uint64t bus address and the uint64t device. And then we have the void enumerate function, which takes a uint64 device address and a uint64 function. Alright, inside of our enumerate PCI function, we need to get the amount of entries inside the MCFG to get the ACPI device config. Now we need to create the struct for the ACPI device config, so we'll jump back into ACPI.h and we'll create our new struct, device config, and we have the uint64t base address, the uint64t PCI seg group, the uint8 start bus, and the uint8 end bus. And then we have a uint32t reserved. And we'll just make sure that this is packed as well. Now this device config is the configuration for the everything about the PCI, the base address of its configuration, and the start and the end bus. Okay, so this actually needs to be uint16 PCI seg group, not uint64. So now we can do int entries equals 2 brackets MCFG dot header dot length, go out of 1 bracket minus size of ACPI : MCFG header, go out of both brackets, and then divide it by size of ACPI : device config. So that gets the amount of device configurations that we have, and then we can iterate through all of those. So for int t equals 0, t less than entries, t plus plus, then we can get our ACPI config, which is similar to the way that we got the MCFG. So ACPI : device config new device config equals casted to an ACPI : device config pointer, 2 brackets uint64t, go out of 1 bracket MCFG, plus size of ACPI : MCFG header, go out of 1 bracket, plus bracket size of bracket ACPI : device config, go out of 1 bracket times t. So that was pretty full on, so I'll try and explain that a little bit better. This needs to be a device config pointer. So we're getting the base address of the MCFG, adding the size of the MCFG to get the end of it, and then adding on the size of the device config times by the index to get the base offset of the device configuration. Right, now we can iterate through all of the buses in the device. So for int uint64 bus equals new device config dot start bus, bus less than new device config end bus, bus plus plus. Now we can do enumerate bus new device config base address, comma bus. Alright, so that's our first enumeration function done. Now we need to do the enumerate bus function. So now we need to calculate the offset of the bus address from the base address. So uint64t offset equals bus bit shifted to the left by 20. And then we can do uint64t bus address equals base address plus offset. Now we need to map the memory of this address, so we need the page table manager. We need a global page table manager. So in our page table manager.cpp, we can define a global page table manager. So page table manager global PTM, global page table manager, or you can do g underscore page table manager. I'll do g underscore page table manager equals null. And then we need to use this page table manager in place of the old page table manager that we were using. And of course that we also need to declare this in the page table manager header so that we can access it elsewhere. This is an extern. Alright, now in kernel util.cpp, instead of creating our own page table manager here, we need to use the global page table manager. So g underscore page table manager equals such and such, and replace all references to the old page table manager with the new one. Right, now we can get back into PCI.cpp and return to what we were doing. We need to include our page table manager. So include paging / page table manager.h. Then we need to do g page table manager.map memory, casted to a void pointer bus address, casted to a void pointer bus address. So we're just identity mapping this address to itself. Now we need to get the PCI device header. Now we haven't defined the PCI device header yet, so we'll hop on over into PCI.h and we'll create the struct for that. Struct PCI device header. And we have a uint16t vendor ID. This is the ID of the manufacturer who created the device. We have the uint16t device ID, and this is the ID of the actual device created by that vendor. We have the uint16t command, uint16t status, uint 8t revision ID. Then we have the uint 8 program interface, so prog.if. Then the uint 8 sub class, uint 8 class. Then we have uint 8 cache line size, uint 8 latency timer, uint 8 header type, and uint 8 BIST. So we have 4 16-bit values and 8 8-bit values. Alright, make sure we have the semicolon at the end. Now we can head back into PCI.cpp and declare a pointer of that type. So PCI device header, PCI device header equals casted to a PCI device header pointer. This needs to be a pointer as well. Bus address. Now we need to check if the device ID is null. So if PCI device header dot device ID equals 0, we can return, which means this device is not valid. Or if the PCI device header's device ID equals 0xFFFF, that also means it is not valid and we need to return. Now that we have the bus of the device, we need to go on and enumerate through the device. So for uint 64t device equals 0, and there is 32 devices on each bus, so device less than 32, device plus plus. And we can call enumerate device. Pass in our bus address and the device number. Luckily for us, the next two functions are basically copy and pastes of the first one, so just copy all that and paste it in the second one. Change the offset to device, a bit shifted to the left by 15. Change this base address to bus address. Change this bus address to device address, and all references to bus address to device address. Change this enumerate device to enumerate function. Change this device to function. Make sure that we spell function correctly in the function definition. Alright, now that we've switched all those over, we can go on and change this function to 8, because there is 8 functions per device. And now we can copy everything up to the checking if the device ID is valid, and paste that into enumerate function, because the function is the last endpoint in our pyramid of devices. So the offset is now function. Bit shifted to the left by 12. The function address now equals the device address plus the offset. We need to map the function address to the function address, and the PCI device header equals the function address. That's it. We've gone through the entire table of PCI devices. Now in kernel util.cpp, inside of our prepare ACPI, we need to call our PCI enumeration function, so make sure that we include our PCI.h. And now we can do PCI : enumerate PCI and pass in the pointer to our MCFG table. Right, now that we have that, inside of our PCI.h, just to make sure that we've done everything correctly, we can print the device ID and the vendor ID to the screen to see what devices we're dealing with. So we can do global renderer. For that we need to include basic renderer. Basic renderer.h. Then we can do global renderer.print to h string, which we need to include c string. So include c string.h. Now we can do to h string. PCI device header dot device ID. Now we can print a space, and then we can print the vendor ID, or rather we can print the vendor ID and then the device ID, and then we can do global renderer dot next. Now, as you can see, at the top left of our screen, we have our vendor IDs and device IDs. So we have 8086 for the vendor ID and then 29C0. 8086, I believe, is an Intel vendor ID. Then we have 12341111, which is the device ID and the vendor ID of the QEMU graphics controller. And then we have a couple other controllers as well. So we can look these up on the PCI lookup table website and see what they are. So the 8086-29C0, let's have a look what that is. So as you can see here, the 8086-29C0 is the Express DRAM controller. So that's pretty cool. Now that will be it for this video. In the next video, we will create some lookup tables to be able to convert these vendor IDs and device IDs to actual descriptions so that we can have a more detailed output of what devices we have in our system. And we might also start diving into how to create a controller for one of these specific PCI devices. So that will be pretty interesting. But for now, thank you for watching and I will see you next time.